Non-constant acceleration occurs when the acceleration itself is changing. So the rate at which its velocity is changing is itself changing. So here's an equation of position where we have 4t cubed minus 6t minus 2. And in this equation, the acceleration itself is changing. So we're going to look for three different things. How far did it go from 0 to 2 seconds? How fast is it moving? And what's its acceleration? So to figure out how far it went, that's actually pretty easy. So we have 4t cubed minus 6t minus 2. So how much time elapsed? That's going to be 2 cubed minus 6 times 2 minus 2. And if we do the math on that, we end up with 18 meters. So that's how far it traveled. How fast it's moving, we need an equation for velocity. But for velocity, we're starting with position. And we know that position is 4t cubed minus 6t minus 2. That's x. Well, if we take the derivative of x with respect to time, that's going to be the velocity at any given time. So what's the first derivative of this equation? Well, we do the power rule, so that's going to be 12t squared minus 6, and this is just going to be 0. So that's our velocity. So if velocity is equal to 12t squared minus 6, all we have to do is put in our numbers. So that's going to be 12 times 2 squared minus 6. And that gives us a velocity of 42 meters per second. So the last question, what is its acceleration? Well, we know that its velocity is 12t squared minus 6, and we know that acceleration is the first derivative of velocity. So all we have to do is take the first derivative of this. So what's the first derivative of 12t squared? That's going to be 24t, and that becomes 0. So the acceleration is 24t, or 24 times 2. So the acceleration is 48 meters per second squared. Keep in mind, that's the acceleration at an instant. In this case, the acceleration is changing. We are going to do this problem set, and you can download all of these questions from the link within the description. As always, if you enjoy, like and subscribe. Okay, so the first question says we have the position of the object given by this equation, and the question is, what's the instantaneous acceleration of the object at 3 seconds? So our equation, 3t cubed plus 1.5t plus 4.5, that's x. And so if we want to find acceleration, we have to take the second derivative of position. So what we're going to do is we're first going to take the first derivative, which is dx dt. So that's going to be 9t squared, doing the power rule, plus 1.5. Now, the second derivative is going to be acceleration, or the first derivative of velocity. So we do our first derivative, and that's going to give us 18t. So what's the acceleration at 3 seconds? That's going to be 18t, or 18 times 3, and that's an acceleration of 54 meters per second squared. Let's try another one. So they give us a position function, of 3t squared minus 12t, and it says, when does the object stop? Well, the object is going to stop when the velocity becomes 0. But we don't have an equation for velocity, we have an equation for position. So we have our 3t squared minus 12t, and that's x. And if we take the first derivative, dx over dt, that's velocity. So that's going to be 6t minus 12. So what we need to do is figure out when that velocity v becomes 0. So we have 6t minus 12, but we want that to become 0. So we just sub in 0 and solve for t, bring the 12 over and divide, and that gives us a time of 2 seconds. Okay, in this one we have a velocity function of 8t, and the time interval is from 5 to 10 seconds, and the question is, what's the displacement? Well, if our velocity is given as 8t, and we want displacement, then we need to take the integral. And displacement is equal to the integral of velocity with respect to time. But we're going to do this from a bounds of 5 seconds to 10 seconds. So what is that going to be? That's going to be delta x is equal to the integral from 5 to 10 of 8t dt. So what do? We add 1 to the exponent, so that becomes 2, divide by the new exponent, which is 2. 8 divided by 2 is 4. So our displacement is going to be equal to 4t squared, but we have to do that from 5 to 10. So that's going to be final minus initial, so that's going to be 410 squared minus 4 times 5 squared, and that comes out to 300 meters. So our displacement, or change in x, is 300 meters. Here we have an acceleration value changes according to this formula 2t minus 6. During a time from 3 to 5 seconds, how much does the velocity change? So we're going from acceleration to velocity. Well, what is that? Well, we know that change in velocity is equal to the integral of acceleration with respect to time. So we have to integrate the formula for acceleration. So that's going to be the integral of 2t minus 6. And we're doing that from 3 seconds to 5 seconds. So what's the integral of 2t minus 6? That's going to become t squared. We add 1, divide by the new exponent, so that becomes t squared. And then we have to add 1, and really what we have here is t to the 0, right? T to the 0. So add 1 to the new exponent, which becomes t to the 1, divided by 1. So that ends up becoming minus 6t, and that's our change in velocity. But remember that we have to do this from 3 to 5 seconds. So what is that? That's going to be 5 squared minus 6 times 5. And then that's our final, minus our initial, which is going to be 3 squared minus 6 times 3. So all of that is our final, and all of that is our initial. Remember, that's what the bounds are, final minus initial. And when you do that, you get a change in velocity of 4 meters per second. Okay, this question's a little bit different because we have initial conditions. We have a car with an initial velocity of 20, and we have an initial position of 100. So we have to take this into account, and you're going to see where this is going to come from. This is going to come from the constant, which you've learned about when you've done integrals. So we have the acceleration as 4 minus t, and the first question is, write an equation that represents velocity as a function of time. So for part A, we have v equals the integral of a dt, and that's going to be the integral of 4 minus t dt. Now, the integral of 4 with respect to time, dt, is going to become 4t. And minus t, we add 1, becomes squared, divided by 2 is a half. So that's going to become 4t minus 1/2 t squared. But this is velocity, and it has an initial velocity. So when we write our equation, this v is going to be 20. We have to include that initial velocity. That's our constant, our plus c, plus 4t minus 1/2 t squared. Now, if you haven't gotten to integrals yet, that may not make sense, but in calculus, whenever you do an integral, you also have to add a constant, because if we had done the derivative of this, this would have gone away. In all of the other problems we've done so far, that initial value was 0, so we didn't have to worry about it. So here's our answer. B, write an equation that represents the position as a function of time. So we know that now we have to do the integral, this time, of velocity with respect to time. So that's going to be the integral of 20 plus 4t minus 1/2 t squared. And all of that with respect to time. So 20 is going to become 20t. 4t, that's going to be squared divided by 2, so that's going to become 2t squared. And then this is going to become a 3, so that's going to become cubed, divided by 3, so this will become 1/6. But the position doesn't start at 0, it starts at 100 meters. So we have to include that as our constant in our equation. So that x is going to be 100 meters as our initial position, plus 20t, plus 2t squared, minus 1/6 t cubed. When does the maximum velocity occur? So if you think about this, the acceleration at t equals 0 is 4. It's positive. So the car is speeding up initially. But as time goes on, this is going to make this acceleration value decrease. So as the acceleration decreases, even though it's going down, the velocity is still going up. Think about it. If that decreased to 3 meters per second squared, it's still positive. It's just not speeding up as quickly as it was initially. That's a very tricky idea, but it's a very important one. So I'm actually going to write that down and say that the max velocity occurs when acceleration is 0, because it's going to speed up with a positive acceleration all the way until the acceleration becomes 0. So we can say that the acceleration is equal to 4 minus t, and that's going to occur when acceleration is 0. So solving for t, that just comes out to 4 seconds. And then finally, it says what position of the car, what is the position of the car when it reaches its maximum velocity? Well, it reaches its maximum velocity when time equals 4 seconds. So all we have to do is go back to our position formula, which is 100 plus 20t, I'm just going to go ahead and put the time in, 4, plus 2t squared, that's going to be 4 squared, minus 1/6 t cubed, or 4 cubed. And if you do the math on that, the position, the change in position, or the final position, is going to be 201.3 meters. Now, the final question is, sketch the graphs of the acceleration, velocity, and position with respect to time. So let's just think about acceleration first. The acceleration starts at 4 and decreases with time until it gets to 4 seconds, at which point the acceleration is 0. So what does that graph look like? Well, it starts at 4 meters per second squared and it's decreasing. But what's the velocity doing as the acceleration is decreasing? It's still positive acceleration, so it's speeding up, but the rate that it's speeding up is decreasing. So we know the initial velocity was 20 meters per second. So it starts at 20 meters per second. The slope of the line at this point is actually equal to the acceleration, 4 meters per second squared, over here. So as time goes on, the velocity increases, but the rate at which it's getting faster is decreasing. So it's speeding up from 20 to 28, but the acceleration is decreasing. When it gets to this point, the slope of the line is 0, meaning the acceleration is 0, but it's at its maximum velocity. So what's 28? That's v max. So in the final graph, we have position. Well, what does it do? It starts at 100 meters, that's our initial position. This isn't quite to scale here. And it ends up at 201.3 meters. Well, what happens to the slope? The slope starts out at 20 meters per second, and it increases until it reaches this maximum velocity of 28 meters per second. The rate of change is going to be, at any point, the velocity, which is equal to the velocity on this graph at any point t.